Hi everyone. Our next topic is universal gates. So we have two types of universal gates. One is NAND gate, and second one is NOR gate. First one, NAND gate. Okay. So NAND gate is nothing but AND gate followed by NOT gate. AND gate followed by NOT gate. Okay. That means inversion of AND logic. Okay. Inversion of AND logic. So what is AND logic? Product, otherwise multiplication. Product or multiplication, that is the logic. Inversion of this product is nothing but NAND. Okay, inversion of this product logic is NAND. Okay, that is the logic of NAND gate. Okay, and the next one, logic symbol for this NAND gate, that is logic symbol. Always you remember, first step is a logic symbol, after that truth table, and after that switching circuit diagram. These are the three steps, okay, for this logic gates. Okay, now logic symbol. So logic symbol of NAND gate, same as AND gate only, but you can add one bubble in front of the AND gate. Okay, already I told you bubble means inversion, right? ఆల్రెడీ మీకు నాట్ గేట్ ఎక్స్ప్లెయిన్ చేసేటప్పుడే చెప్పాను, బబుల్ ఇండికేట్స్ ఇన్వర్షన్ ప్రాసెస్. ఆల్రెడీ నాండ్ గేట్ అంటే మీనింగ్ ఏం చెప్పుకున్నాం ఇక్కడ. సో అండ్కి అపోజిట్. ఓకే, దట్ మీన్స్ అండ్ గేట్ ఫాలోడ్ బై నాట్ గేట్, దట్ మీన్స్ ఇన్వర్షన్ ఆఫ్ ది అండ్ లాజిక్, రైట్? ఇన్వర్షన్ ఆఫ్ ది అండ్ లాజిక్ అంటే అండ్ గేట్ వరకు మీకు ఏదైతే అవుట్పుట్ వస్తుందో ఆ అవుట్పుట్ కి ఇన్వర్షన్ అనేది అప్లై చేయాలి. ఓకే, సో ఇన్వర్షన్ అప్లై చేయాలి అంటే ఒక బబుల్ ని అక్కడ యాడ్ చేస్తే సరిపోతుంది. బబుల్ ఇన్ ద సెన్స్ వాట్? నాట్ గేట్. ఓకే, ఒక నాట్ గేట్ ని మనం అక్కడ యాడ్ చేస్తున్నాం. నాట్ గేట్ అంటే సపరేట్ గా మీరు ఇలా డ్రా చేయాల్సిన నెసెసిటీ ఏం లేదు. ఓకే, జస్ట్ ఇన్వర్షన్ యాడ్ చేసినా అది దట్ మీన్స్ బబుల్ ని యాడ్ చేసినా సరే అది ఇన్వర్షన్ ని ఇండికేట్ చేసేస్తుంది. సో దట్ నేను అండ్ గేట్ డ్రా చేసి దానికి ఇక్కడ ఒక బబుల్ యాడ్ చేశాను కాబట్టి అండ్ ప్లస్ నాట్ గేట్, so which is equals to NAND gate. Okay, so here I am taking two input variables, so that is A and B, and this is our output Y equals to, so AND logic is what? A product B. Okay, for that A product B we can take inversion, that means what? AB bar. Okay, so this bar indicates complement, otherwise inversion process, right? So here the bubble indicates inversion process, indicate inversion. Okay, so this is about NAND logic. Okay, so now, so we can, if we expand this particular logic diagram, then we will get this is our AND gate. Okay, this is AND gate. After that you can take inversion mechanism, that is NOT gate. So this is NOT gate. This is combinedly called as Otherwise you can take like this. Okay, that's better. Okay, this is about NAND gate, AND gate plus NOT gate. So combinedly we can drawn like this. Okay, so this is about logic symbol of NAND gate, and next we can move for truth table. Okay, second one, truth table. Okay, here the input variables are A and B, and the output variable y equals to A B bar. Okay, complement of AND logic. Okay, so already we know two variables means four possibilities, so that is 0 0 0 1 1 0 and 1 1. So these are the four possibilities, right? So already we know the AND logic, right? For AND logic, okay, for AND gate, so if we are taking A, B are the two input variables and the output equals to y equals to AB, right? If we are taking 0, 0, 0, 1, 1, 0 and 1, 1. So these are the four possibilities. So now the output equals to here the product of A and B. So 0 into 0 you will get 0, 0, 1, 0, 1, 0, 0 and 1, 1, 1. So if any one of the input is 0, output will get 0. If both the inputs are 1, output will get 1. So this is the logic of AND, right? So complement of this AND logic. For example, complement of this outputs means what you will get. So complement of 0 means 1, complement of 0 means 1, complement of 0 means 1, complement of 1 means what? 0. These are the NAND outputs, right? NAND outputs. So once you check here, the first possibility 0 0 0 0 product of this AB is what? 0, right? So product of AB equals 0 and the complement of that product equals to what? 1, right? And in the same case 0 into 1 you will get 0 product. So complement of that 0 product equals to 1, and 1 into 0 you will get product 0, complement of that product you will get 1. So and 1 into 1 you will get product 1. Okay, complement of that product 1 equals to what? 0. Okay, so this is about a truth table of NAND logic, right? So if you observe these three possibilities, so first three possibilities, what you can conclude? So if any one of the input is 0, if any one of the input is 0, the output of NAND logic is, otherwise NAND gate, one. In the previous case, what happened? If you take AND gate, if any one of the input is 0, the output will become 0. But whereas in NAND gate, NAND is inversion of that AND logic, right? So that if any one of the input is 0, the output of the NAND gate equals to 1. And if you observe that this fourth condition, so the output of NAND gate equals to 1 only when both the inputs are high. If both the inputs are high, the output of the, sorry, this is 0, right? The output of the NAND logic equals to 0. If both the inputs are high, the output of the NAND gate equals to 0. But when it comes to AND gate, if both the inputs are high, the output also will become high. Okay, but this NAND logic is completely inversion of AND logic, so that you will get logic 0 here. So this is about truth table of NAND logic. And if you observe switching circuit diagram for this NAND logic, so here I am taking this is your AND logic symbol. Okay, this y equals to a into b bar. This inside the box, so we have a switching circuit diagram like this. This is your 5 volts battery. Okay, that means we can call it as source, otherwise input. And when it comes to this load or output of this particular NAND logic. Okay, now so already we know truth table of this particular logic, that is AB bar. So 0 0 0 1 1 0 1 1, and here you will get 1 1 0. So this is your AND logic. So now so మీరు ఎలా డిజైన్ చేస్తే మనకి ఈ 4 కండిషన్స్ ని సాటిస్ఫై చేస్తుంది అన్నది మనకి ఇక్కడ క్వశ్చన్ మార్క్. మనకి ఈ 4 కండిషన్స్ ని సాటిస్ఫై చేసే విధంగా స్విచ్చింగ్ సర్క్యూట్ డయాగ్రామ్ వచ్చేసి ఇంప్లిమెంట్ చేయాలి. ఓకే, ఆల్రెడీ ప్రీవియస్ సెక్షన్ లో మనం డిస్కస్ చేసాం. AND లాజిక్ అని అంటే కనుక మనకి డైరెక్ట్ ఒక ప్యారలల్ స్విచ్ అనేది కనెక్ట్ చేసేస్తే మనకి నాట్ ని సాటిస్ఫై చేసేస్తుంది. ఓకే, సిరీస్ లో 2 స్విచెస్ ని తీసేసుకుంటే మనకి అది వచ్చేసేసి AND లాజిక్ ని సాటిస్ఫై చేస్తుంది. రైట్, AND logic ni satisfy. This is for NAND logic, sorry, not, and this one is AND, right? In case parallel ga manam 2 switches ni construct cheseste ganaka manaki adi OR logic ni satisfy chestundi. This is OR logic ante parallel switches ikkada mention chestunnanu. So parallel switches will give OR operation, and parallel switches combination. Okay, parallel switch will provide NOT operation, right? And series combination of switches will provide AND operation, otherwise AND logic, right? So already we verified these 3 conditions in previous session, right? Now the circuit diagram for NAND logic. Okay, already I told you NAND means AND followed by NOT gate. That means AND plus NOT gate equals to NAND. Okay, this is the logic. Okay, already we know parallel combination of switches, sorry, series combination of switches will provide AND logic, right? Series combination of switches will provide AND logic, but we require additional NOT operation. We require additionally NOT logic. So how you implement this NAND switching circuit diagram? Okay, so whatever the series, so this will provide our AND logic, so this will provide NOT logic. So we require AND plus NOT. That means we can implement that switching circuit diagram like this. Okay, so here we have one switch, here we have another switch, so we can call it as A for this switch, and we can call it as B for this second switch, right? So same, whatever the series combination of switching circuit is there in previous AND gate, that I can take in parallel manner for NAND logic. Then it will be satisfy these 4 possibilities. Okay, once you check whether it is satisfied or not. Okay, one simply says if both the inputs, that means if both the switches are closed, then the output will become logic 0. Why? Because if these 2 switches are closed, then the current will chooses this minimum resistance path only. So definitely this load will having certain amount of resistance. While closing these 2 switches, this entire path having 0 resistance. In that case, the current always chooses the zero resistance path when compared to load. So in that situation, this load will have zero current, so that bulb will not glows. Bulb will not glows means that is logic 0 condition. That means what? If both the switches are closed, then the output will become logic 0 in AND. If any one of the input is 0, that means any one of the input is 0 means definitely one switch is open. If one switch is open means the current will not flow in that particular path. Okay, current always exists only in closed path. Okay, current will not exist in open path. So any one of the switch is open means this is completely open path. In that case, current will not flow through this particular path. So the entire current flows through this particular load condition. In that case, a load will activate it, so that bulb will glows. So bulb will glow means that is equivalent to logic 1. So any one of the 0 condition, the NAND logic is always 1. So then this switching circuit diagram satisfies the NAND logic. So this is for NAND logic switching circuit diagram, right? NAND logic switching circuit diagram. Okay, so this is AND logic, right? Series combination of switches will give the AND logic. Parallel switch will indicate the NOT logic. So here the NAND is nothing but AND followed by NOT logic. So in that case, the series connection of switches will indicate in parallel manner. Then we can get the NAND logic. So this is about a NAND logic. And next we can move on to second gate, that is NOR gate. So which is also similar to this NAND implementation, right? So that is NOR gate is nothing but OR gate followed by NOT logic. Okay. So anyway, we will look into this particular gate here. So the second one here is NOR logic, otherwise NOR gate. Okay. So here OR gate, NOR gate is nothing but OR gate followed by NOT gate, otherwise NOT logic. Okay, that means OR gate plus NOT gate will gives the NOR logic. Okay, so first of all, OR gate means what? OR gate is nothing but which indicates sum, otherwise addition, right? Sum or addition. NOT means what? Inversion. NOT means what? Inversion. That means that NOR gate is nothing but what? Inversion of addition or sum. Inversion of addition or sum. So when it comes to logic symbol, so here this is OR logic. Okay, so for that so here what? Inversion of addition function. So this OR gate will provides addition, right? So inversion of that addition means you can add one bubble in front of this gate. Okay, then you will get NOR logic, otherwise NOR gate. So here we have two inputs, those are A, B, and here we have Y, and up to this we can get A plus B. So because of this bubble, so we will get A plus B bar. Okay, A plus B bar. So this is about the logic symbol of NOR logic. And if we expand this particular configuration, so we will get so here we have OR gate, and here we have NOT gate. Okay, so this is A and this is B, and this is Y equals to A plus B bar. Here A and here B. So here we will get A plus B. So this A plus B is a single input here at this point. Okay, so at this point A is one variable, at this point B is another variable. If you combine with the help of this OR logic, then you will get A plus B as one particular input. Okay, that particular input can be applied to this particular NOT gate. So this input is converted to A plus B bar. Okay, so this is the expansion of this particular NOR logic, right? So this is about logic symbol. Next we will move on to truth table. So first you can take input A and input B and output Y equals to A plus B bar. But already we know our logic, that is otherwise A, B, so Y equals to A plus B. This Y equals to A plus B is nothing but what? OR gate, otherwise OR gate logic. So when you take inputs like 0, 0, 0, 1, 1, 0, 1, 1. So 0, 0 means obviously this will indicate 0 according to OR gate logic, and 0, 1 means 1, 1, 0 means 1, 1, 1 means 1. So this is about OR logic, right? So here NOR is nothing but what? Inversion of this OR logic. NOR means what? Inversion of OR logic. So inversion of OR logic means inversion of this OR output. So what you will expect? So in the case of 0 we will get 1. In the case of these ones we will get zeros. This is completely NOR logic. Okay. Now we check how it will exist. Okay. So 0, 0, 0, 1, 1, 0, 1, 1. Okay. Okay. Now A plus B means what? 0 plus 0 means you will get 0 here, right? A plus B 0. Sorry, A plus B is nothing but 0 plus 0. That will equates 0, right? So inversion of this A plus B, inversion of this sum, that means inversion of this 0 will gives 1 here, right? In the same way, 0 plus 1 means what? 1 according to our operation theorem, right? 0 plus 1 equals to 1. So but inversion of that sum equals to what? 0, right? The same here also. 1 plus 0 you will get 1. Inversion of that 1 equals to 0. So 1 plus 1 equals to what? 1. So inversion of that 1 equals to what? 0. So this will gives our NOR logic. Okay. So from this table, what we can conclude from these three possibilities. So any one of the input is 1, so the output will become 0. If any one of the input is 1, the output will become logic 0. Okay, if any one of the input is 1, the output will become logic 0. So what about the first observation? So how we conclude this first observation? So if both the inputs are zeros, then the output will become high or logic 1. Okay, so this is about truth table of NOR gate. Okay, so these are the universal gates. So why we call universal gates? So universal gates. So we can call So here NAND or NOR gates are called as universal gates. Why we choose these two are universal gates? So what is the speciality of these two gates? Okay, that means with the help of these two gates, we can able to construct or implement any digital circuit. Okay, any digital circuit in the sense which includes which includes basic gates, special gates. Okay, basic gates and special gates. So digital circuit construction completely depends on these basic gates, otherwise special gates. So with the help of these universal gates, we can able to construct these two types of gates. Okay, even not only basic and special, even universal gates also comes into this digital circuit design. Universal gates. Okay. So with the help of these three fundamental building blocks, we can able to design any digital circuit. Okay, but in the case of universal gates, with the help of these two universal gates, we can able to construct these basic types of gates and these special types of gates and these universal gates also. How universal gates means? So with the help of this NAND gates, we can able to construct this NOR gate. Right, with the help of this NAND, we can able to construct this NOR logic, and in the same way, with the help of this NOR gate, we can able to construct NAND also. So in that scenario, we can call it as universal gates. Right, with the help of this NAND, we can able to design this basic gates, special gates, universal gates also. Universal gates is nothing but here NOR logic. Okay, in the case of NAND. Okay, if you take NOR logic, so we can able to design basic gates, special gates, and a universal gate, that is NAND. Okay, so because of that, we can call it as universal gates. If we have only NAND and NOR logic, we can implement entire digital circuit. Okay, that is why we can call it as universal gates. So this is about universal gates. We have two gates; those are NAND and NOR logic. Okay, NAND is nothing but what? AND gate is followed by a NOT logic, that is called universal gate. That means inversion of the product will indicates the NAND logic. Okay, this is a logic symbol first, and the next truth table. So after that, switching circuit diagram. And here, when it comes to NOR gate, so OR gate is followed by NOT logic. That means inversion. OR is nothing but addition or sum. So inversion of that addition will indicates the NOT logic symbol and truth table. And what is the meaning of universal gate? This one. Okay, and next, switching circuit diagram of this particular NOR logic. Okay, okay, so how you will get? So here, what is the logic here? OR plus NOT gate, that means OR gate followed by NOT gate, which indicates the NOR logic. Okay, okay, so you can, so already we know OR logic is nothing but what? So this is your switching circuit diagram. So this is your bulb, load, and these two switches are connected in parallel. Right, parallel switches. And already you know about NOT gate. So what is the NOT gate construction? So one parallel switch will gives the NOT logic, right? This is NOT. So combination of these two will provide the NOT logic. Here we have parallel connection, parallel switches configuration, and this is the parallel switch. So if you take this parallel switch configuration in parallel mode, then we can get our NOR logic, right? How you indicate this? So if you take this is about two parallel lines, and this is your load, otherwise output terminal, and this is your 5 volts battery, so which is called as a source or input terminal, Okay, now you can indicate your parallel switching configuration in parallel mode. Okay, in that scenario what happened? So you will get right, this is your switch A and switch B. Okay, then you will get your combination. So you can verify with a truth table also, like A and B. So Y equals to A plus B bar. So 0 0 0 1 1 0 1 1. So you will get 1 here. So you will get zeros here. Yes, you can verify this particular truth table whether it is satisfies or not with this configuration. Okay. So this is about switching circuit diagram for NOR logic. Okay. In the next session, we will discuss about special gates or extra gates. Okay. Thank you.